Can you hear me? Cool. Okay. Good, good. I had to restart my router like right before this because my internet went out, and so I'm a little nervous. But we'll see what happens. How are you all doing?
Very cold.
Yeah. So I don't know, I mean the wind is it's mostly wind chill. But yeah, I mean, I don't know about you. I'm kind of glad it's cooled down for a little, but I know it's supposed to be in like the upper 80s again in the next few days. So yeah, it's supposed to be maybe, yeah, by Friday, Saturday, Sunday, it's going to be pretty hot again. So guess it just depends on what you like. But it turns out the fact that the wind is doing this is kind of a nice segue into our talking about depositional environments and like what gets certain sedimentary rocks to form in certain places and in certain ways. So as much as I'm afraid that this is going to like knock out my internet connection again, I'll talk about what we'll do if that happens once it's officially 2 o'clock. But it's kind of good segue. Because as it turns out, we've certainly got some small class transportation going on out there, but also, as it turns out, the shape of the mountains, like actually the fact that the mountains are where they are, is actually largely what contributes to these winds being as strong as they are. Unfortunately, we don't have a lot of time to get into the causes of Santa Ana winds in this class. That's more something, if you want to take my California geology class in the spring, we'll talk about that. Or if you want to stick around at the end of class, if my connection holds up, we'll talk about that then. But anyway, I guess it is 2. So hopefully you all have stable conditions and connections and can all hear me. So today we're going to finish up with our stuff on sedimentary rocks. So we have our third lecture that's just straight up on sedimentary rocks before we get into some more specifics. So if you've looked ahead at the syllabus at all, we have a lecture on mass movements, which is landslides and avalanches and stuff like that on Wednesday. Then Monday, we're doing rivers and streams. Wednesday of next week is glaciers, and then actually right after that is already our third test. So I know it feels like it's pretty fast, but time feels very nonlinear in general this year. So so just as a heads up, our next test is actually Monday, November 9th. And then we don't have class on Wednesday the 11th because it's Veterans Day. So that's just kind of the shape of things for the rest of this unit. So today I ended with this slide last time, and today we're gonna start elaborating more on the conditions in which these different things form. And then in those next few lectures that I just mentioned, we're gonna go into more detail still on some of the specific conditions. But before I go on, actually, before I even ask you if you have questions, I just want to give you a heads up. I had to restart my router right before this class. My internet connection is not enjoying this wind, and I know I've had a few other people email me about the same thing. If you get disconnected, don't panic. If you just get disconnected, do not panic. As usual, these slides will be up after class. This video will be up after class. So it'll be accessible to you, and you can also always ask me questions. But if I get disconnected, which I really hope not, I will just hang on. I will email you from my phone if my internet goes down. And so I'll just keep you posted from there and either let you know when things are back and we can start again, or if it's really bad, we'll figure something out. But hopefully hopefully we won't need to go there. But just if the meeting suddenly stops, that means that my internet connection died, and I guess I can try to use a phone hotspot. We'll get there when we get there. Hopefully we won't get there. But does anyone have any questions about logistics or about stuff from last time or about just any general concerns, questions, clarifications before we go on. Cool. All right. Okay, and if you do think of anything, just as always, like you can just say it. You don't necessarily have to like do your raise hand in here, or you could type it in the chat. Oh yeah, so after class today, again, this video will go up, these slides will go up on Canvas. There will be another quick quiz, but I, again, didn't get that up before class because my connection was down. And then there will also be both the vocab and the sort of note-taking and study guide for the mass movements landslide stuff. That will go up right after class as well. So just keep an eye out for that, although it might not be quite as immediately after class as usual, depending again on what my internet connection is doing. Still clear? Anyone got anything before we go on? Whoops, that's not, didn't mean to, no. All right. So last time we went through kind of how we classify clastic sedimentary rocks. We walked through the different stages of forming them, of the weathering, erosion, transportation, deposition, and lithification, and talked about different characteristics that we use to qualify and describe clastic sedimentary rocks. And so if you remember, there is some mineral component, like we will describe, like you can differentiate between different kinds of sandstone, for example, based on what minerals the sand grains are, or you might differentiate between different kinds of things like conglomerate and breccia based on what the cement holding them together is made out of. But for our purposes in this class, as far as sedimentary rocks go, we're not going to talk too much about the chemistry, because the major classification is how rounded or pointy the clasts are, how big or small the clasts are, and how well sorted. Are they all the same size and shape or not, are they? Because that's really what's going to tell us about the conditions that transported and deposited those rocks, rather than about the source of the material. So in today, what we're going to actually talk about is a lot of the situations where that stuff gets deposited and formed into rocks, and where you might expect to find these different things based on kind of what's going on there. So today I'm going to actually, a lot of the slides are going to be something where I want you to just think about the environment that I ask you about, and kind of just think about from a, just like if you were to go to that place and like say you were just going to a mountain stream, for example, and looking at it, or you just going to the beach and looking at it, like what's going on there? And then try to think about just what you might see in that place and apply it to how that could mess with rocks and form rocks. So just use your standard sense of observation is just a really important part of geologic thinking. Just very much is, what do you already see and know about this place? And then just go, okay, and what could this do to rocks and minerals? So we're gonna spend a lot of that on today. So there will be a lot of examples today. Don't worry too much if it feels like a lot, because many of them we're gonna address in a lot more detail in those individual lectures about landslides and about rivers and about glaciers. But anyway, just be familiar with these names of rocks, especially conglomerate, breccia, sandstone, these guys over here, because we're gonna bring them up a lot. And I want you to sort of think about where those are gonna form. But anyway, so recap one more time. We went through these 5 steps of clastic sedimentary rock formation. So hopefully this slide looks extremely familiar now, because I think it's in this slideshow like 6 times. But weathering, erosion, transportation, deposition, and lithification. You need all of those things to happen to form a sedimentary rock. But ultimately, what controls what ends up in any individual specific rock in a specific place is deposition, because it can't become a rock if it's not sitting still. That lithification process requires compaction and cementation. It requires being squished and sticking together, which this stuff can't do. Sediment can't do that if it's still moving. So ultimately, the deposition is really the boss of what ends up in any specific rock. The other 4 steps are going to determine what happens to individual clasts, but those are clasts. The rock that you're going to pick up in the field, a rock you're going to get an example of, an outcrop you're going to look at, to try to piece together that story of how the Earth must have created this situation. Those are going to all be post-deposition things. So really today's focus is going to be on deposition, but with some degree of how did that stuff get transported there. So does that make sense so far?
Yes.
All right, and if it stops making sense, just feel free to ask. But anyway, deposition. So we're going to give you another extremely literal term, because definitely get used to thinking literally. It will never hurt you here. A place where sediment is deposited is called a depositional environment. So you're going to see that term, depositional environment, a lot in your book. It's something that it is a phrase you will see on this quick quiz and on the test. That just means, where did the sediment get off the bus? Where did it stop moving? And so just thinking about that, what are some kinds of places where you think sediment might get dropped off by its transportation mechanism? You can either say them or type them.
Could it be at like the end of a waterfall, maybe?
Yeah, so the end of a waterfall, definitely. Rivers, absolutely. Yeah, I mean, there's a reason we've got a whole lecture on rivers. Valleys, yeah, and definitely there's different kinds of valleys too that have different, like a valley that's controlled by a river versus a valley that's controlled by a glacier are going to have very different characteristics and very different rocks. What are some others you can think of? And if you're having trouble thinking of some, just think about the transportation mechanisms we talked about. An ocean, absolutely. So ocean is a big group. There's actually, depending on where in the ocean you are, you're going to get different stuff going on. And so we're going to talk about that today, not in a huge amount of depth. That was not an intentional pun, I'm sorry. We're not going to go in a lot of depth on the deep ocean, but if you are interested in that, if just the little bit that we go into about that today is really cool to you, there are other classes in our department. Like if you need to fulfill another science gen ed, we have several whole classes related to the ocean. Any other thoughts? Or what kind of environment? Rifts. So rifts are valleys, and depending on whether they're in the ocean or on land, you're going to get different behaviors on them. But yeah, let me ask you this: where is this wind coming from? Like what kind of environment are we sort of almost in here in Northridge? Or I guess I'm in Northridge, in inland Southern California. Yeah, mountains and desert. Yeah, those are two I was very much looking for. So the desert is absolutely a very specific environment, and mountains can both be their own thing and can also be controlled by the wind and water and ice that act on them. So these are all really, really good things. I'm glad you came up with these because we hit the nail on pretty much all of the big ones. If it will let me advance the slide. So when we talk about depositional environments, again, most of what you said is actually everything that you said is on here, which is awesome. And there are a few more. Some of these words might seem unfamiliar, but we'll get to them. But when we talk about depositional environments, we generally break them into 2 groups. So terrestrial, meaning on the land, and marine, meaning in the ocean. And I guess extraterrestrial could also be on the land, although I don't know if you're following the cool news about the moon, but we'll talk about that later. Anyway, terrestrial is on land and marine is in the ocean. And so it's important to note that terrestrial depositional environments absolutely still do involve water. In fact, almost all of these have water as one of the major, if not the major, both transportation mechanism and deposition mechanism, and for that matter, erosion and weathering mechanism. So while you might think of the desert as landy as land can get, there's still sometimes water involved depending on the particular desert at the particular time of year. Glaciers, I mean, ice is water, but worth noting again, streams and rivers and lakes, even though they are water, these count as terrestrial because they're acting on the surface of the continent. Even a really deep lake is still something that exists on the surface of the continent. These are still things that are shaping continental plates, or I guess volcanic islands that might be on oceanic plates, but to the point where they're land. So really that division is not just is water involved, but is the ocean involved. So if the ocean is not involved, it's terrestrial. And so these marine settings, so an alluvial fan is, we'll define that in like 2 slides. But it's because it's better explained with a picture, so do not worry. But yeah, marine, you know, if it's in the ocean. Okay, cool. And we're going to go through all of these. But before I do that, any questions? Do all of these seem like familiar things except for an alluvial fan? Like, do any of these others? Yeah. So really a way to think about that, yeah, pretty much, is to go, you know, kind of everywhere. You can have sedimentation kind of everywhere, which on the one hand is like, whoa, everything is a depositional environment and that doesn't narrow anything down. But as we're going to see, the specific characteristics of every single one of these places, there are certain things that work, certain things that are in action, and you can tell by what the rocks are like whether a thing was formed in one of these places or another. So sedimentation might be everywhere, but it's different depending on where you are. And so that's how, like, you can tell, like, there's some places now, like, again, in my background image, that is in the Colorado Plateau in Utah. And all of that is, it's actually marine and lake sediments. It's all like deep water sediment that is now the desert. And so the stuff that's happening on the very surface of it now is desert sedimentation. But there's enough evidence just from the shape and texture and content of these rocks that we can know, even though they're the middle of the desert now, even though they're as dry gets now, you can tell that used to be in the ocean based on the characteristics of those rocks. And so that's also why, in addition to just like the layers that we use, like we talked about way at the beginning of class, of just telling the order things happened by the order of the layers and what has or hasn't happened to them. You can also tell, okay, where did this happen? Was it on the land? Was it in the water? Just based on the characteristics of that. So does that make sense? Cool. So as the wind-driven sedimentation goes on outside, I was originally going to start with the water ones. But I figured I should actually start with the desert. Shuffled the slides because of the Santa Ana winds going outside. So start with the terrestrial environments. Start on land. So wow, that picture was not that pixelated when I put it in here. I'll see if I can replace that with a clearer picture before I upload this. But just looking at this desert, so just what do you see? Dunes, yeah. So those are, go ahead. Sorry.
I just said sand dunes.
Yeah, sand dunes. This is a major thing going on here. Now, not all deserts are made of sand dunes entirely. Like the Mojave isn't mostly sand dune, but there are places that still have them. And this is definitely like, if you're gonna set a scene in a desert in a movie, you're gonna show some sand dunes and maybe cactus. So this is like your archetypal desert. So looking at these dunes and looking at this sand, what do you think the main thing transporting that sand is? Wind. Yeah, that's a lot of instantaneous correct answers. Awesome. Yeah, so wind is really the boss in the desert. There are some desert conditions that we'll talk about later that are actually still pretty water dependent. But when you're talking about sand dunes, you're talking about wind. And so thinking about what the wind can carry or not, just look outside for inspiration. What do you think the class size involved is going to be, depending on what the wind is doing? Yeah, they'll be really small. And why is that? I mean, just think about the weight, right? Get out of the trash. Yeah, the wind can't carry bigger clasts because it's wind. I mean, again, it's very much a weight factor. And again, we should all be really glad that the wind can't carry bigger clasts because we would be in a lot of danger in weather conditions like this right now. So yeah, in a sand dune setting, I mean, the name sand kind of says it all. The sand is what's there, and everything that's smaller than the sand. So the sand is small enough that the wind can kind of push it around without necessarily picking it up. But anything that's smaller than sand is actually going to get picked up and carried away. So like what we're getting right now isn't sand. It's things that are like silt or clay or mud size, really, really, really tiny clasts. Whereas even though the wind out in the desert is going to be stirring some of the sand up, the sand isn't going to flow all the way out to the San Fernando Valley. So the desert and especially dunes are primarily a wind-driven environment. And because the wind can pick up big stuff, small stuff, but not big stuff. So what's left behind is the well-sorted sand. Basically, what's left behind is the stuff that the wind can't pick up. And in general, it's pretty much the same size. When you compress sand, as the name implies, you get sandstone. And because the wind does a really good job of sorting out what it can and can't carry, you're going to get very homogeneous sandstone. You're going to get something that if you pick that up and we're like really into being organized and symmetrical, you would look at that rock and go, this is the most organized and symmetrical set of sand I've ever seen. It's great, if that were your thing. And that's just because of what the wind can and can't do. You get some differences in texture depending on which side of the dune you're on. If it's the side the wind is blowing across versus the side on the other side of the crest of the dune. We're not going to get into that a lot here, but that's a thing that can happen. And another thing that can happen with the wind is, the wind blows in certain directions, but it's not always going to blow in the same direction. Like, again, if you think about the wind we're having right now versus the wind that we normally have. Normally, the wind in Northridge is going to come from the ocean and blow towards the mountains. But right now, in this kind of Santa Ana wind condition, the wind is starting from the east and blowing to the west. It's going in the opposite direction. And also just any kind of weather condition can change even a little bit of the angle the wind is coming from. And so in some wind-driven desert conditions, you might get patterns called crossbeds. So if you see this thing, like what's going on here? So layers are happening here. But are these the like nice flat layers that you would see if in like a textbook, like in a slice of the Grand Canyon or like in my background image? Yeah, no, they're super all over the place. And this actually represents just rapid changes in wind direction, not just necessarily changing the way things pile up, but also kind of scraping at the surface too. So when you see cross beds, that means you have rapid flow that changes direction a lot. So in this case, that's you can sometimes get this in water too, but it's a really big thing that happens in wind-driven desert kind of conditions. And another thing you can also get are actually ripple marks. So these are, you would more commonly think of a ripple associated with water. And actually, I think this, to be totally transparent, I think this photo is one that used to be water. But if you look at, so I know this looks like awful pixels, and I'll try to find out why this image turned so low res when I went full screen. But if you were to see this at high res, you would see that these things that look pixelated actually are ripples. The wind, because it is a flowing fluid, it's just fluid air rather than water, can make ripples in the sand. And so you can get features like this that form on desert rocks and wind-driven rocks, as well as in places like the bottom of rivers where you have flowing water. So does this make sense? Turn on RTX. What is RTX? I feel like I should know what that is, but I don't. Okay. I guess I have failed you. Does this make sense? Okay. Cool. Okay. So by the way, these things are, if you look at the study guide, note-taking guide, when I talk about like sedimentary structures, like stuff like this is what I mean. Like dunes are a sedimentary structure, but also cross-bedding is a structure, ripple marks are a structure. And so even though I put that as a bullet point on the sedimentary rocks sheet, we're gonna address different structures all through the next few lectures on glaciers and rivers and landslides as well. So just kind of keep that in mind. And I'll try to use the word structure, sedimentary structure, every time we get to something like this. But are we good on deserts? If you ever go out to the desert again, which is to say, I think you're not going to get coronavirus in the open desert. If you need to get outside, go to some places in the desert and just see what you can see. But anyway, let's move on. There's a bunch of these to get through. So alluvial fans. So this is the one where this was probably, was there anyone in here who has heard this thing before? Has anyone has heard of an alluvial fan? Oh, you have. Okay. Oh, in lab. Okay, good. So I guess 102 is ahead of me now. But anyway, so for those of you who have heard of this, what is it? Rather, just looking at the shape of this thing, at least do you see why it's called a fan? Yeah, so it's at the end of a stream.
Oh.
Yeah, go ahead. Sorry.
I was just gonna say maybe water went through there.
Yeah. So water absolutely came down this steep canyon, this steep notch in the mountain and spilled out, carrying a bunch of sediment. And you see it's shaped like a fan, right? Like if you're, like one of those unfolding fans, like a paper fan, where it's very narrow at the point where it exits the canyon that the stream is flowing down, and very wide at the end as it spreads out and rolls out into this valley. And so this is actually an example from pretty close to here. And actually, once you know to look for these, they are all over the place. Like if you drive along the 210 and look towards the mountain, well, if you were a passenger in a car driving along the 210, don't do this while you're driving. If you look over there, you're gonna see all kinds of stuff like this at the base of the mountains, and people build houses on them even. But you'll see this very characteristic, fan-shaped thing that is thicker at the base of the mountains where it comes out, and then also thins towards its edges. And so this, if you were saying the end of a stream coming through a canyon, that's exactly where this is. That's exactly what's going on here. And so the word alluvium means sediment that's deposited by a stream. But it's important to note it's not a stream that is constantly flowing. In a place where there's a stream that's flowing all the time, you're actually going to call that something different, which we'll get to in a few slides. So alluvium is like the water flowed and it dropped it off there, but the water is now gone too. And so this is also actually particularly common in desert environments, because you'll get a thing where it rains a lot in the mountains and the rain just courses down the mountains and brings a lot of stuff, but then it dries up and leaves behind things like this. You get them in wetter environments too. You get them anywhere where you have water flowing out of the mountains, but they're particularly prominent in deserts where you might get a lot of water at once and it dries up quickly. Yeah, you probably have seen them on hikes. There are really a lot of them around here. And this is one of those, once you know what to look for, you're gonna see them. But yeah, it's a sediment deposited by a stream. So the transportation here is it's water, but also gravity. Like this is a really stinking steep mountain, right? And this is a very flat valley. So some of it is water pulling this down, but gravity definitely aids both the water flowing and collecting, but also stuff continuing to fall that might have just been loosened by the flowing water. And you get these where the mountain intersects the flatter valley or plain. So this is a really, really stark contrast. But it can happen at less sharp contrasts as well. Although actually the interface between the San Gabriel Mountains here in LA and the LA Basin, the San Gabriel Valley, is actually one of the steepest mountain versus valley contrasts like in the world. It's certainly one of the steepest in an urban interface. So we're pretty remarkable here in LA from a geology standpoint. But anyway, because you've got a steep mountain and you've got both gravity and rapidly flowing water working here, you can get some pretty big chunks. You can get some pretty big clasts going on here. And but because they all get deposited kind of at once with the water just stopping, they're all going to get piled up in this same thing. And so where you have so you're going to end up with stuff that's poorly sorted, a mix of big clasts and small clasts. And so if you remember when we were talking about, rounded versus angular, if that mountain front is longer, if it's traveling further, it might get smoothed out enough that you end up with conglomerates, because that's where your component clasts are kind of rounded. Or if it's just kind of a short, quick fall and it just kind of shatters and stops, you're going to get breccias, which are more broken up and pointy. And in some cases, yeah, you can get sandstones in there too, depending on, you're still going to get some water trickling a little further than other places. But for the most part, this is going to be kind of poorly sorted, messy looking stuff. And also very often these shapes will be preserved. So not only if you find a breccia that's associated with an alluvial fan, you're not just going to go, yeah, that's a breccia, so it comes from an alluvial fan. That's not a good conclusion to make, in fact, because you can get breccia in a lot of places. But you'll probably also see like the remnant of this structure. And so you can get a better sense of that. But yeah, just keep an eye out next time you're going like literally anywhere in Southern California. You'll probably see these. Anyone have any questions about this? Cool. If you think of any, as always, just dump them in the chat or on the forum, now that there's a forum. Anyway, let's move on. So glaciers have very specific environments as well. And this is going to be a major topic for next week. So I'm going to just do this one pretty quickly. But yeah, as the name would suggest, it's ice that's doing all the work here, water that is frozen, but still flowing as a frozen sheet. Glaciers have some really interesting physics to them, in addition to just being something that can drag along stupidly large rocks. They can drag along like house-sized boulders. And they'll leave them in very, very specific shapes. The valleys that are formed by glaciers make very specific shapes. You'll get piles of things that have a specific sorting pattern and also just a specific shape on the landscape from glaciers dragging in and out. And so just kind of remember that. You're going to get big piles of poorly sorted stuff in very specific patterns. And we're going to talk about that for an entire lecture next week. So that's all I'm going to say about that one for now, unless you have a question about it right now. Has anyone here actually seen a glacier? Nope. So if you're interested in seeing a glacier, there are still some in the Sierra Nevada if you go on the eastern side. They are shrinking because climate change is real. But if you want to go see them, they are there. But more on that next week. Yeah, and this is actually a picture from Eastern California as well. Honestly, this is like one of the best states you could ever hope to be in to talk about geology, just because we have so many different environments. But again, not a lot of time for that in this class, but 344 if you want more of this. Moving on. So you notice both mountain streams and rivers were on that list. And so another name for things where you're dealing with flowing water is called a fluvial environment. More often you'll hear that associated with larger rivers, but technically anytime you have a flowing stream and you're talking about transportation and deposition within the stream or its stream bed, you're going to be having a fluvial environment. And so just looking at these two pictures, your mountain stream on the left and your river on the right, what are some differences that you see? Just as
The
yeah,
river's more smooth.
yeah, the river's smooth. The water's moving at different speeds. The mountain stream is absolutely more aggressive, although you probably wouldn't want to jump in the middle of this river either. But yeah, that idea of water speed, and I actually really like the term aggression for it. It's not a technical term, but it's a good way to think about it in terms of the aggressiveness of the water. Because this could be, you know, because in this case, it's flowing very fast and very hard. And you can see here, there are some big old chunks in here. Like this boulder didn't just like fall there because it fell there. No, this probably got broken off and moved there in a really intense, aggressive flood or flow. Whereas here, you might not see any rocks sticking out at all. And yeah, this is probably deeper, but there's still very different things going on here that are directly related both to how much water is there to begin with and how fast it's moving. And again, that aggression thing is a really nice way to think about it. Like, imagine something like a wolverine, which isn't super big, but will totally fight you at the drop of a hat. Yeah, that's dangerous. Whereas something like let's say a cow, like it's just gonna be chilling, but like it's big enough that it could still cause a problem, even if it's fairly docile. So kind of that kind of comparison. But now thinking about this difference in flow speed and water volume and aggression, what do you think that might do to the resulting rocks? Yeah, so that fish, oh yeah, those fish that eat coral, they are definitely a weathering agent. But thinking about the left picture versus the right picture here, what kind of clast sizes do you think these might be transporting?
Maybe bigger clasts for the faster moving stream and smaller ones for the slower stream.
Yeah, exactly. Very much exactly. And if you remember on our slide about classifying clastic rocks, that pretty much the biggest classification is the size of the biggest clast. So yeah, in your mountain stream, you've got fast water, big clasts, and the amount of sorting kind of depends on the slope. Because if you remember, how well sorted something is has a lot to do with where things get dropped off, what can or can't be carried. So the slope will affect that a lot. While as in a big river, you have slower water. It can only carry smaller clasts because it's slower. But actually, in something like this, you get different flow speeds at different points across the riverbed. So things will probably be moving faster in the middle than on the sides. You'll have different depth. And so the sorting is actually going to depend on where you are across the river. You'll have some things that are floating, some things that are being dragged along the bottom. The position in the river makes a huge difference. And so that's also part of why with these two things, with flow rate, with position, with the difference like regular river behavior versus flood behavior, that's why we're going to have a whole lecture on that next week. So we're going to stop there for that now, but these can get pretty nuanced, even though you might go flowing water's flowing water. But any questions about these for now?
Yeah, can you remind what do you mean by the sorting depends on slope?
So we'll get more, well, actually, don't worry, you don't remember because I didn't talk about that much yet, but basically, the sorting of something depends on how, like what's falling out of it where. Like if something, if you remember, we talked about, in this case, like if the water is flowing at the same speed like at a certain speed, it's going to be able to carry some stuff and it's going to drop everything else. And so as it slows down, it's going to drop different things at different times. And so you might expect like all of the big stuff to be at the top because that's where it's flowing the fastest. And then as the slope gets more gradual, it's going to start flowing slower and is going to start dropping stuff that's smaller and smaller. So the rate at which the slope changes, like if it goes really abruptly from being near vertical to near horizontal, you're going to get a very different looking, like more stuff is going to drop out at once than if it gradually gets slower and slower and slower. And then you kind of get bigger stuff, sort of big, smaller, smaller, smaller. Does that make sense?
Yes, thank you.
And next week, we're actually going to talk about that a lot more. Next week, we're actually, there is going to be an equation about slope and river size and flow speed. And we're going to sort of tie that in with what it can carry, but it's like a very simple equation. So it is math, but it's not scary math. So just heads up. But any other questions about this? Cool. And if you think of some later, again, we've got a whole class on that next week. But lakes are actually, again, you might think of a lake, yeah, that's water. But that's still considered a a terrestrial environment, because again, it's on a continent. It's water that is on the land and surrounded by the land. And so another word you might see for that is lacustrine. I'm not going to use that word, but your book, I'm going to say lake. But your book, or if you're interested in this and start reading more about it elsewhere, you'll probably see fluvial for rivers and lacustrine for lakes a lot more. So just, that's what that means. But just thinking about lakes, what's controlling transportation and deposition? And what rocks do you think you'd get because of that? How is
Maybe-
sediment? Oh, go ahead.
Sorry, maybe animals?
So animals can certainly bring some stuff into that lake. But
It's not like the main thing that brings rocks there.
No. Well, let me ask you this. What brings the water into the lake?
I actually don't know, so I'm going to be quiet.
Well, just want to guess? Anyone want to guess? How do you think? Well, so rain is part of it, but if it were just rainfall, you would need kind of an exorbitant amount of rainfall. But also, why do you think the water is piling into lakes in certain places and not others? Yeah, so ice melt from the mountain. So if ice melt from a mountain, what does that turn into? Man-made lakes are very much a thing, and that's very much its own thing. We're not so much going to talk about man-made lakes. I mean, the deposition that happens in them is similar, but let's say it's a natural lake. So this ice melt from a mountain thing that Mario said in the chat is really on point. So if you think about the ice melts and it comes down the mountain, what is it coming down the mountain as?
Water?
Yeah, as a mountain stream, right? Like we just talked about those. So generally, a lot of lakes have an inlet, like they have some sort of source that is either a stream or just melt coming from downhill. So in this case, there doesn't seem to be an obvious stream, but you notice how around this lake, everything is up higher. You can get, rain can collect in a lake, or snow melt can connect in a lake. You can have streams collecting in a lake. They generally form in places that are at the most downhill thing in their vicinity, because water is going to flow downhill as a stream, as collected rainfall, as ice melt, as all of those things. So the transportation then is the water, right? Because if all of those things are flowing down land, they're going to pick up chunks of stuff. But now let's say that water ends up in the lake. Who here's like been swimming in a lake or boating on a lake or something? Okay, so you have, what was the water like? Very cold. Yeah, that's fair. I went swimming in Lake Ontario once, and whew, yeah. But aside from the cold, how was the water? What was the water moving like, or was it? Yeah, it kind of stays still. That's exactly right, Elaine. If the water's staying still, then the thing that's going to cause the sediment can't be transported anymore if the water's not moving. So actually the deposition here is not flowing water, it's gravity. It's the stuff falling out of the water and onto the floor of the lake because there isn't any transportation anymore. So gravity is still gravity, even in the water. But thinking of this idea of sediment just very slowly falling down through the water to the bottom of a lake that just isn't moving, what do you think the rocks would be like there? Like, are they going to have big clasts? Are they going to be really chunky? What do you think?
Can you repeat the question, please?
So what do you think the clasts are going to be like? Like, are you going to have big, chunky, angular clasts in the bottom of this lake? Or is it going to be smaller and finer and more rounded?
I want to say because of it's a mountain stream that'll be big, chunky, angular clasts.
So it could be in association with a mountain stream. And so there is some variability. But now think about something like this lake where we don't actually see a big stream coming into it. Like, think about what could just rainwater trickling down a hill carry with it.
Finer grain,
Yeah.
smaller rocks and stuff.
Yeah. So in that case, like if you did have a mountain stream like an actual stream partly feeding this, you would see the bigger chunks right next to where that stream comes in, because the second it hits the water that's not moving, it's just going to go. But these smaller particles, these smaller grains have more chance to just trickle down and settle at the bottom of the lake.
Okay.
So lake environments are, oh, sorry, were you going to ask something?
No. I was just agreeing with you.
So lake environments are actually really gentle. It's generally, the transportation comes from streams or rain, but the deposition is just gravity. And you get these very fine-grained, well-sorted rocks, because generally it's only the fine stuff that can be picked up and carried in. So in this case, you're going to get things like mudstone or shale. And so both of these are consolidated from the very, very finest grains of sediment. The difference is that mudstone is just kind of a chunk, and shale has more clear layers in it. So you see how this is just, I mean, they're similar looking brownish gray rocks. They have a very similar surface texture if you were to touch them both. But shale is going to have these layers a lot more than mudstone is. But does this make sense? Today is the only day we're really going to talk about lakes. So there will be fewer questions about them on tests and stuff, but ask your questions now or email or office hours if you got them. Cool. Or ask them later if you think of them. Moving on. So that was all we were going to do for terrestrial environments. And actually what's cool is a lot of those environments people recognize in extraterrestrial settings too. There's maps of especially Mars, but there's stuff people are finding on the moon where you can see not liquid water so much, but like evidence of a lot of these environments existing, which shows the evidence of liquid water in the past. So a lot of the same geologic principles you can use to piece together history on terrestrial Earth, you can do on extraterrestrial other planets if your imagery is good enough, which I think is super cool. But anyway, any questions about any of the terrestrial stuff before we go into the ocean? Cool. Let's hit the waves, I guess. So of these marine environments, the first one we're going to talk about is a delta. And so is anyone who's heard of, I guess you all said you'd pretty much heard of these before. So is there anyone who hasn't heard of a delta like at all? You haven't. Okay. So a delta, the most famous one, like you think about like your whatever year you had world history, like the Nile River Delta or the Amazon River Delta. You might hear a lot about the Mississippi River Delta. Basically what a delta is, it's always the something river delta. And so it's a place where a river meets an ocean or a gulf or a large body of salt water. You have a flowing freshwater stream emptying into a vast saltwater body. In some cases, it's a weird freshwater body. We have the Sacramento River Delta in California. In that case, the Sacramento River kind of empties into sort of a weird goopy wetland that flows into San Francisco Bay, but that's kind of a weird one. For the most part, you have usually a pretty big river, they can be small, but a flowing freshwater stream emptying into a saltwater body. And so you have two very different kinds of bodies of water interacting. And what happens is as the river flows out into the ocean, that river's carrying a lot of sediment. Especially when it's a large river that has a lot of tributaries, a lot of smaller rivers that flow into it, which is something we'll talk about a lot more next week. Usually by the time a large river meets the ocean, it's going to have a ton of water in it. And that water is going to be able to carry a lot of sediment. Even if it's small sediment, it's going to be able to carry a lot. And so as it flows out into the ocean or the Gulf or the bay or whatever, and the flow speed changes, that river isn't going to be able to hold the sediment anymore, but it's still, the flow is going to be able to carry it out to some degree. And so like if you look at this picture, this is the Atchafalaya River Delta in the Gulf of Mexico. And you can see that like there's a green, so even though that this river is flowing out into the ocean, it carries the land with it. As these streams finger out into the ocean, there's land along them. And that's not from that river cutting into the land. It's actually land created by sediment falling out from the river and accumulating along the points of flow as those flowing points get slowed down by the larger body of water. So does that general idea make sense? Yeah.
Professor,
What, yes?
oh my gosh, can an example be from like the Malibu rivers going down to the ocean, or is that not?
Yeah, I mean, it's a smaller river, so it's going to be a much smaller delta. But anytime you have a river entering the ocean, you're going to get something like this. Yeah, but just like the really big ones are associated with like the Mississippi, the Nile, the Amazon, like the largest rivers make the largest deltas. But yeah, there are small, I mean, Southern California is not the best place to see these, but we do have them. And actually the reason they're called delta is from, they're sort of vaguely shaped like the Greek letter delta, which is basically just a triangle. A capital delta is like that. But if you kind of look at the way how this starts narrow when it leaves the land and kind of spreads out. Can you all see that? I realize I'm using red on green. Is this okay for everyone? Or should I switch colors? But yeah, kind of get this Greek delta shape, which is why they named it that. I mean, I guess they could have just called it a triangle, but it's a delta. So I guess I kind of gave away these points in explaining what this is, but what do you think is controlling the size of the clasts that can get here to begin with?
The speed of the river?
Yeah. It's the speed of the river. Let me write this in here just so this isn't a confusing thing when you look at this later. Yeah, so the speed of the river is what's controlling that. So if you have, and so the speed of the river might change. Like in a year where it's a big flood, you might have a faster river, which can carry more stuff that's bigger out further. Where if it's a really dry year, you're gonna have less stuff that goes less far, that's smaller. So you can actually get a pretty big range of sizes of stuff in a delta because of that. But then regardless of the size of what's getting pulled out there, what makes it stay there? Why doesn't it just keep flowing out into the middle of the ocean?
Is it the current of the ocean?
Yeah, so the current or the lack thereof. Because even with currents, like usually that river, that channelized river is going to be going faster. And so very often it's just the ocean or the bay or the Gulf or whatever isn't going fast enough. And so the stuff just falls. It's a similar idea to what we were just talking about with that mountain stream entering a lake, except it's a much, much larger scale. But basically it's another sort of almost basically gravity. The flow speed gets slow enough that gravity pulls everything down. So what you're going to get in the delta, just to reiterate that, the class size depends on what the river's carrying, which depends on how fast it's going. The stuff in the class is going to depend on what it flowed through. So you could get very different chemical composition, very different minerals, depending on where that river goes. For something like the Mississippi, again, that goes all the way from Minnesota to Louisiana, you're going to get a huge number of different things it passes through. So it just really depends on what's along the way. Deposition happens when the flow stops. And because all of these things are variable, the flow speed depends on the weather and the rain and the climate, the class content depends on different things along the way, all through the watershed. Deposition, like where does the flow stop? It's going to vary from year to year. So you can actually get a wide range of different kinds of rocks in a delta. And so in that case, you're going to want to look for actually larger scale landforms and sort of to indicate that this is what's happening here. Does that make sense? Any questions about deltas? I think if you were interested in more ocean stuff, I'm pretty sure they talk more about this in the oceanography class. The person who teaches that is a sedimentary rock specialist. So if this is really cool to you and you need another gen ed, I would look into that. But yeah, if you don't have more delta questions now, I'm going to move on. If you think of them, just go ahead and ask. Moving on, the beach. So this is a very big, important, significant sedimentary environment. This is a major depositional environment that forms specific things. So just think about the beach. We've all been to the beach. We live in Southern California. What's doing the transporting and what's doing the depositing? What is making sand? Not a trick question. Yeah. So fish that eat corals can contribute to that, but what is the main thing going on? Yeah, the waves. The waves far more than the wind. I mean, the wind contributes to the waves. The waves that you get at the beach are wind driven. They're tide and wind driven. But really the thing that's making the sand is not so much the wind. It's the waves just repeatedly pummeling, just whap. Like, I don't know if any of you have even, like, has anyone ever not even necessarily boogie boarded or surfed, but just tried to swim in the ocean and missed and just gotten face planted by a wave? I mean, even a little wave can just pound your face into the ground, and it's not pleasant, even just a little wave. And so if you imagine that sand cannot run away, it's just there. And over time, the waves just over and over, just crashing into the ground, are going to break everything down into really tiny, really even chunks. And so where did that rock get there from? I mean, it could be stuff from corals, although that actually will come up a little more. It could be things weathering and falling off this cliff, for example, due to gravity. A lot of different things can bring that source material to the beach. Like in Hawaii, it's volcanic rock that gets pummeled into little bits. It kind of just depends on what's there, but just that repeated, percussive, just waves crashing over and over and over again breaks everything down and into small chunks. And in general, they're very rounded because even though they're not necessarily transporting very far, this isn't a case where, like, I know I said for the most part, the more rounded something is, that means it's traveled further. In this case, it's not so much that, it's just, it's been there longer. It's been in that, trapped in that sort of push of the ocean, that pulling back and forth, but also just the pummeling over and over. And so you get these very even, generally very rounded sand grains. Like next time you go to the beach, whenever we're allowed to do that again, hopefully it won't be, hopefully by next summer, just look at the sand. Like if you put sand in your hand, like it's not going to be, it's generally not going to be sharp little shards. They're generally going to be quite rounded just because of that repeated, incessant pounding from the ocean. And so you get a lot of sand. It's the beaches, it's sand. That's like you go to the beach for the ocean and the sand. Ocean makes the sand. What kind of rocks do you think you're going to get? And think literal. Literal is good. Sandstone, yes. Sandstone comes from sand. Super not a trick question. In general, like if you look at the names of those sedimentary rocks, sandstone is made of sand, siltstone is made of silt, mudstone is made of mud. Conglomerate, a conglomeration is just a mix of stuff. Breccia implies broken, so you have little broken chunks. All of the names of these are super, super literal. So like if you're not sure, and you just think like, wow, there's a whole mix of stuff there. That's a conglomeration of stuff. It's a conglomerate. Or man, that fell off a cliff and broke into a bunch of pieces and turned into a rock. Broken, breccia. The beach is made of sand, sandstone. Like seriously, it is that literal. It is not a trick. Like remembering that, you'll be in awesome shape for sedimentary rocks. It's not even like a mineral structure kind of thing like with igneous. It's just like, what is it made out of? But yeah, whoops, at the beach, whoop, where I lost a slide. I lost a slide. Yeah, at the beach, I gave it away. I'll put that slide back, but it's the ocean is doing the transporting and depositing. It's beating up the clasts and you get sandstone. I will put that slide back. I don't know where it went, but does anyone have any questions about the beach? Cool. So then our last ocean environments are actually really like in the ocean way out there. But you have different behaviors depending on whether you're just under shallow water versus when you're in deep water. So differences beyond like normal like clams and stuff and like freaky sea spider beasts. There are actually differences in what's happening with the sediment and the rocks as well. So just thinking about the environment closer to the shore versus smack in the middle of the ocean, what do you think some differences might be?
The sand in the shallow side looks more loose compared to the one in the deep ocean.
Yeah, so it is. And why do you think this might be kind of looser, considering it is still sediment piling up?
Because of the pressure?
So there is less pressure. But what else? So that's part of it. Yeah, the tide. There's more motion. There's both less pressure and more motion in the shallow ocean. Really, in terms of the waves and the tides themselves, like that tends to manifest the most right at the coast, right at the beach. But in terms of currents and stuff, you still have a lot more action in that. You still have a lot more impact of wind on the water and of current behavior in shallow water. In the deepest deep ocean, it is extremely still. There's very little going on there. There's a lot more movement in shallow water. And so you're going to end up with some pretty different stuff. In addition to like your fish that eat coral are going to hang out in the shallower ocean because that's where the coral is. That's where most sea life is because a lot of stuff can't exist at the really crazy pressures that are at the bottom of the ocean. And if you want some like super spooky in time for Halloween stuff, look up the stuff that lives this deep in the ocean because it's all really weird, but not a topic of this class for the most part. But thinking about just the difference of more versus less motion, what do you think some differences in the rocks and the shallow versus deep ocean might be? What kind of clasts do you think might be moving around in the shallow versus deep ocean? Are they both going to be able to move things that are the same size? Yeah, they're not. So which one do you think is going to be able to move bigger clasts, the shallow or deep ocean? Yeah, the shallow, because that's where there's more movement. Yeah, exactly. So there's still both conditions where they're ultimately the deposition is controlled by gravity, is controlled by sediment falling down through the ocean. But the size of that sediment and the stuff that's in it is really what varies more. So shallow ocean, less waves, still currents. And so it's still going to be well sorted and well-rounded small clasts because of what can and can't move around. So you're going to get sand and silt, and this is also where you're going to get a lot of fossils. This is an area where most of the marine life is really vivid. Your coral reefs are going to exist in the shallow ocean. A lot of fish and shellfish and stuff is going to be here. Whereas at the deep ocean, most of what's falling down there is stuff that is plankton, is small shells, is stuff that is just trickling down through miles of water to pile up at the very bottom. And so you get the very, very finest grained stuff at the bottom of the ocean because the bigger stuff is actually, it's just not there. It's already hasn't even been pulled out that far. So you're going to get silt and clay, and then also the shells of a lot of dead marine critters, both the stuff that lives down there and the stuff from way, way higher up in the ocean. But these are the places in the ocean and also in some big lakes where you get the big expansive sheets of thick layers of different sedimentary rocks. Again, kind of like in my background picture. That's where you're going to get things like this. It's just the specific characteristics. Like either way you'd go, yeah, that formed in the ocean. But you would look at the details of the size of the clasts, the shape of the clasts, and what else is in there to tell whether it's deep or shallow. So does that make sense? See no objections, so I'm going to move on. All right. So so far, like all of today, all of last class, most of the previous class, we've been extremely focused on clastic sedimentary rocks. All of that, weathering, erosion, transportation, deposition, lithification is clastic process. All of these deposition environments, they're hinge on deposition. They hinge on things being clastic. But if you remember, there are actually three other kinds of sedimentary rocks. And the reason I'm saving these for now when we're talking about environments of formation is that these other three form all in very, very specific settings. As we just talked about, you get clastic rocks in a ton of ways, in a ton of places, and they're still indicative of where they formed, but you can get similar things in different places. But these other three kinds of rocks very, very much depend on extremely specific conditions. So if you find that kind of rock, that condition has to exist. So I'm going to go through these three now, and you're going to find there's not a lot of them. So yeah. So biochemical sedimentary rocks are consolidated from shells of shellfish, of plankton, of coral. I guess you could have some fish bones in there, but in particular it's shells. Because if you remember way, way, way back when we were talking about how minerals form, and about even though a mineral has to be something that can form by geologic processes, it can't be something that only forms by biological processes. there are certain organisms that can make carbonate minerals, can make things that are just are minerals that are in their shells. And so biochemical sedimentary rocks have that material in them. So does that make sense to start?
I have a question.
Yeah.
Do like bones count for that or no?
Generally, no, because they have some different compounds in them.
Got it.
It's pretty much shells.
Okay. Thank you.
But you'll find bone fossils you can find them actually you're most likely to find those in clastic rocks, because if something just dies and gets covered by sediment, then yeah. So biochemical, it's generally limestone. So most of what we've talked about in this entire class so far are silicate rocks, where silicon is the main, that silica ion is the main thing going on. But there's a whole other class, the second most common class of rocks are carbonate rocks, where they have this carbon and oxygen thing going on. And so clams, oysters, snails, other things, scallops, pretty much if it's shellfish, that's what it is, have this in their shells. And so when they die, those shells are pretty heavy and they're just going to fall to the ground and lithify. And so you can have a situation like on the left where it's pretty broken up. Or you can have a situation on the right where you have these nearly completely intact shells in a matrix of smaller sediment. And so the only difference here is really, it depends on the force of the water again. Like in this case, this is probably something that formed closer to the shore, or something where there was much more active involvement of waves breaking down stuff so that it's not recognizable. Whereas something like this is more likely to have formed deeper in the ocean, or maybe even in a lake, places where this stuff is just going to settle down and mud is going to fill in around it. So in this case, you might take this apart and find that most of the material is actually shell remnants. Whereas in this one, like you've got the shells are super obvious, and that this other stuff probably isn't shell material at all. So really the degree of which it looks like it's shells depends on how it was weathered and beaten up by the water. But both of these count as biochemical limestone because they're made of this material and it was sourced from shells. And that's kind of what there is to that one. So does that make sense? I knew someone who had a countertop made of this looking stuff once. It was really cool. And anyway, basically, in order to get this, you have to have a place where shells can pile up. And that's going to tell you, very specific things about the environment, like especially if you know things about the kind of animal that had that shell. Oh yeah, and you can also, another example is biochemical chert, which is the same kind of idea, except it's plankton shells, and there actually are silicate plankton shells. And these pile up usually in the deep ocean, but it's the same idea. The stuff dies and it piles up. And this example is actually from San Francisco. You can see a lot of this stuff in the Bay Area. Used to be deep ocean stuff that's now up on land, but just same idea. The next kind, so the difference between biochemical and organic might not seem initially clear, especially since that whole, like, if it's minerals, it can't have been alive. But organic sedimentary rocks have a lot of carbon-rich material that was once alive, but then also other minerals. And usually this carbon-rich material undergoes some sort of state of change, some sort of it's not a metamorphic rock. I'm not going to say metamorphosis, but it's going to undergo some chemical reactions and structural changes to become part of a sedimentary rock. And so if you hear about fossil fuels, like you've all heard of fossil fuels, right? That's where this comes from, because in that way, like your carbon-rich stuff, it's fuel. It's where you get your oil and your gas and your coal, and fossil because it's dead stuff. So there's two major classes of organic sedimentary rocks. You got coal. So here, this coal, it's this dark black band is coal, surrounded by other stuff that isn't coal. And this forms in a very, very specific condition where it's stagnant water with not a lot of oxygen. So like a swamp, basically. And dead plant material just piles up and it mixes, it gets piled up and covered with more rock-based sediment. And because there's no oxygen, that stuff can't rot and decompose properly. So it just gets covered with other sediment. And once it gets covered under several kilometers, several miles of sediment, it gets compressed into coal. And so coal is anywhere from 40 to 90% carbon, 40 to 90% plant-based material. But the other 60 to 10% is generally carbonate stuff. It's generally clay or quartz. But it's just basically a swamp where this stuff can't rot. Does that make sense? The other one is oil shale. Oil, another big source of fuel. So this is another case where you have you need a certain low oxygen environment where a lot of stuff is piling up and not rotting. But in this case, it's actually fats and proteins. It's kind of different parts of the organism that are piling up and remaining behind. And so in this case, if the environment is low oxygen enough, that stuff can't rot either. And it mixes in with the mud. Rather than necessarily getting covered by it, it gets mixed in. And then when that mud lithifies just in the usual compression and cementation way, that organic stuff turns into a goop called kerogen or kerogen. And in that, you can process that to extract oil. And so if you were to crack open some oil shale, it's gonna like ooze some black stuff. And that's kind of what this is. And so you actually find a lot of this, a lot of it is in lake environments, a lot of it is in swamp environments, but there's some stuff like this in the sort of Orange County area. There's certain beaches like near Huntington Beach where you can just step in oil goo because there were environments like this in the past, even though it's a coastal beach now. So does that make sense? So we have 1 minute. In that 1 minute, do you want me to go through these last 2 slides about chemical rocks, or would you like me to start with that at the beginning of next class? Next class. Okay, that's a strong call for next class. Okay, so next class then, I will still put up these slides today. And there will be a quick quiz still up today, and we'll finish with the last 2 slides about chemical rocks, chemical sedimentary rocks, before we start on landslides and mass movements. So with that, if you're free to go, we're done for today. Keep an eye out in the next like 15 minutes for all of the, excuse me, the quick quiz, because I need to look at it again to make sure there isn't a question about chemical rocks and the new vocabulary. Well, excuse me. If you do have any questions, I'm happy to hang out and take more questions. But if not, I will see you Wednesday or at office hours tomorrow.
Thanks.
Everyone have a good one. You all have questions, or are you just kind of hanging out?
Just hanging out.
All right. You taking notes, or you just?
I was just taking notes real quick. Sorry.
Right on. So just let me know when you're done, and I can turn things off. And also, these slides will go up today.
I am good. Thank you, Professor. I was just
Right
taking
on.
notes.
And I will see you Wednesday. Eli, you got a question, or you just chilling? Okay, I'm gonna take that as just chilling. If you did have a question, just feel free to email me at any time. And I will see you all Wednesday.